So, in this video, I'd like you to calculate this definite integral here. It may be that you know already off by heart the indefinite integral of 1 over 1 plus x squared. On the next slide, I'm going to derive it. So if you'd like to, you could practice trying to derive it to remind yourself where it comes from. And after you've had a go at this, I will see you again on the next slide and give a detailed solution. Okay, welcome back. Let's look at it on the next slide. So this is the integral that we want to calculate, and I know how to integrate this off by heart because I remember it, but let's just assume that we don't know what the integral is. And we can't do this by inspection. If there was an x in the numerator, you could do it by inspection. It would be a logarithm. So instead, if we look at it, we see here 1 plus x squared. 1 plus x squared cannot be factorised because it's always going to be greater than or equal to 1. So cannot be factorised. But you do know the identity that 1 plus tan squared theta is sec squared theta. It's a standard trigonometric identity. It's just cos squared plus sine squared is 1, all divided by cos squared. So let's try and use that. Let's say that x is going to be the tangent of theta. So 1 plus x squared will be 1 plus the tangent squared of theta, and we could write that as sec squared theta. And I'm going to draw a triangle here. X is the tangent of theta. Theta is an angle, and the tangent is the opposite over the adjacent, so it's x over 1. And by Pythagoras' theorem, we can write out what the hypotenuse is. So we square this side, 1 squared, 1, square this, x squared, add them together, 1 plus x squared, and that's going to be the square of the hypotenuse. So the hypotenuse is going to be the square root of 1 plus x squared. And we just pause and just check in our heads, yes, the sides of the triangle satisfy Pythagoras' theorem. And this shows us that we're on the right tracks with this change of variables, because one of the sides of the triangle, and with a tangent substitution it is the hypotenuse, is the square root of 1 plus x squared. So now, we know that x is going to be the tangent of theta. We're going to need the derivative, and dx d theta is the derivative of tangent, which is sec squared. And now it's always helpful to write out the formula you're going to use. The integral of a function of x with respect to x is going to be the integral of the function of x rewritten in terms of the new variable, which we're calling theta. And then you multiply by hand by dx d theta. And then you integrate with respect to the new variable. Now, there are two ways of doing this. One is algebraically. So you could say 1 over 1 plus x squared is 1 over 1 plus tan squared theta, and that's sec squared theta. Or you could just look at the triangle and say that the cosine of theta is 1 over the square root of 1 plus x squared, and therefore 1 over 1 plus x squared is the cosine squared of theta. So I could have just written here cosine squared of theta. That's the same thing. Either way, what we see is that these two things are going to cancel. So sec squared here and sec squared here will cancel, and we're going to have the integral of 1. What about the limits? So the limits here are in terms of x, and here I want to write them in terms of theta. So if x is equal to 1 at the upper limit, then we have 1 is the tangent of theta. Theta is the arctangent of x, it's the arctangent of 1. That means it's the angle that has tangent 1, and that's pi over 4. So at the upper limit we have theta is pi over 4. This is how the arctangent is defined. Of course, there are infinitely many angles who have tangent equal to 1, but the arctangent is defined in this way, that you get this value. And when x is 0, theta is the arctangent of naught, and that is going to be defined to be the angle theta is 0. So we're integrating from 0 to pi over 4, 1 with respect to theta, and you can integrate that and say it's theta between pi over 4 and 0, or you can just say that it's the area of a rectangle and write it straight down. Either way, you are going to get pi over 4. So our result for this integral is pi over 4. And the first thing to note about that is it is positive, and that's good, because if you look at our integrand is positive. We're integrating from 0 to 1, something positive. We're expecting a positive result. So on the next slide, I'm going to look at how we can bound it to check it a little bit more carefully. But before I do that, let's just quickly go through what we've done. So we saw here we had 1 plus x squared. And anytime you see that in the denominator or a square root of 1 plus x squared, you should be thinking about making a tangent substitution. I always recommend drawing a diagram, and one of the sides of the triangle, and for a tangent substitution it's going to be the hypotenuse, should involve the square root of the factor that is making the integral difficult. And then we just use this formula, tidy things up, and hope we have an integral which is easy to perform in terms of our new variable, and in this case it is. And on the next slide, I'm going to show how we can bound this definite integral a little bit more precisely. So, and I want to talk about bounding this definite integral. And to do that, we want to sketch the integrand 1 over 1 plus x squared. So when x is 0, this is at 1. And as you increase x, you are dividing 1 by something larger, so it is going to become smaller. So it's going to do something like that. It's always going to be positive. You just have 1 divided by a larger and larger positive quantity, so it is approaching but never reaching the x-axis. We also notice that this is an even function, so if I replace x by minus x, it does not change the function, because you would have 1 over 1 plus and then minus x all squared, and that is of course exactly the same as 1 over 1 plus x squared. So we have this shape here which is symmetric about the y-axis, and that is typical of an even function. So what does this definite integral mean in terms of the graph? Well, we've said when x is 0, the function is at 1. When x is at 1, we can see the integrand is at 1 over 1 plus 1 squared, so it's at 1 over 1 plus 1, it's at a half. So the integral is going to be the area under this curve from x is 0 to x is 1. And I'll just roughly shade that in here. Now, to bound it, what we can do is we consider an area which is definitely greater than the integral and an area which is definitely less than the integral. So I'll just sketch the upper bound first. So for the upper bound, let's consider the following. We draw the axes. I'm just going to draw it over roughly our range of integration. X, y. This is at 1, and our integrand looks something like this. And this area is less than the area of this rectangle, which has height 1 and base 1. So I can draw that roughly in the following way. I'll just draw it like this, then down here. And this is a rectangle of height 1 and base 1. And that area, this pink shaded area, is greater than this. So we see that our definite integral is less than the area of this rectangle with height 1 and base 1. So it's less than 1. And similarly here, for a lower bound, well, we know that the smallest value of our integrand is going to be a half. So we can tell with certainty that the area of the integral here is going to be greater than this area, which I'm now shading in here. And this is a rectangle of height 1/2 and base 1. So its area is a half times 1. So in this way we see that the value of the integral is less than 1 times 1, and it is greater than a half times 1. So the value of the integral is going to be between a half and 1. And on the previous slide we obtained pi over 4, and pi is a little bit bigger than 3. So pi over 4 is a bit bigger than 3/4, and that indeed lies between a half and 1. So our result for the integral, it's not just that it's positive, it also obeys these bounds. So on the next slide, I'm going to draw some more general consequences and also consider the differentiation of the result for the integral, and we'll look at that now. So on the previous slide, we saw that with our tangent substitution, this change of variables, if we integrated 1/1 plus x squared, it gave us theta, where theta is the arctangent of x. And therefore, writing this out just in terms of x, we have this relationship here. And that, I think, is a very useful integral and worth knowing off by heart. Now, any integral gives you a free derivative. If you differentiate the integral, you should obtain the integrand. So this tells us that the derivative of arctangent must be 1/1 plus x squared. Again, that's well worth knowing, but it's exactly the same result, really. There's nothing new about it. If you know one, you know the other. So what I'd like to do to complete the video is just to calculate this by differentiation. So let's say y of x is the arctangent of x, and we want to find its derivative. We take the tangent of both sides. We're using implicit differentiation. So we get the tangent of y, and that is, of course, really the tangent of y of x. It is a function of x. And on this side, the tangent of the arctangent of x is just x. Differentiate both sides. Here we use the chain rule. Sec squared, derivative of tangent, the same argument, y of x, and then from the chain rule we must multiply by the derivative of the argument, so that's dy dx, and on this side, of course, we obtain 1. We divide both sides by sec squared y, so we get dy dx is 1 over sec squared y, but we have our identity that sec squared y is 1 plus tan squared y. So we know that tan of y is x, so we obtain that our derivative, the derivative of arctangent, is 1/1 plus x squared, and that is the proof of that. And if you know that, you know immediately that the integral of this is going to be equal to the arctangent. So anytime in an integral where you see the square root of 1 plus x squared, you should be thinking about making a tangent substitution. And this is, I think, the simplest example of it. With that, I'll stop this video.